This is our first episode in finite element method. But okay, I'm gonna straight away start with question 2. Question 1 is a first principles derivation of the global equilibrium equation, which is not the main focus of this course. Okay, the main focus of this course is to use the finite element method to solve for, let's say, nodal displacements in a problem or the external loading uh, on a given system. Okay, without further ado, let's get started with this tutorial. So let's read the problem. For the spring system in problem 1, derive the global equilibrium equation by assembling the element equilibrium equations and verify that you get the same equilibrium equations in problem 1. Okay, so we're given these spring constants and the loading P2 is -10, P3 is 20. Assume consistent units for these parameters. Okay, the reaction forces at 1 and 4 are R1 and R4 respectively. Okay, so the simplest problem for any FEM introductory course is a spring mechanism like here, what you see. Okay, later on we will learn about various types of elements, but for now, we will confine our discussion to springs, and in the next tutorials we will talk about other types of elements. Okay, so in fact, this question is beginner friendly because they told you how to do this, how to do any FEM problem in general. Okay, so the first step you do in FEM, right, is you always label the elements and the nodes. Okay, first thing you do is you always label the elements and the nodes. And in this question, they already did it for you. Okay, so they already labeled this as node 1, node 2, node 3, and node 4. And also they labeled the elements for you. The elements are simply the structures or devices between the nodes. So for example, spring 1 is the first element, spring 2 is the second element, spring 3 is another element, and spring 4 is another element. Okay, so they already label the nodes and the elements for you. Okay, normally they don't. So you have to do it yourself. Next, what do you need to do in FEM problems? The next step is to label the uh, nodal displacements and nodal loadings. Okay, nodal displacements and nodal loadings. So, uh, what this means is, okay, what we're gonna do is we're gonna copy this diagram out. Okay, we're gonna copy this diagram out. Okay, then this is 1, 2, 3, 4, and then this is element 1, 2, 3, and 4. Okay, at the so what's the difference between the structure that they give and the structure that I drew? The difference is that, well, I removed it from the walls. Okay, so notice that this entire spring mechanism is attached to two walls, right? I'm talking about this wall here and this wall here. Okay, so I basically removed them from the wall and just let it out like that. And then these these forces that you see here, here, are the externally applied loadings. Okay, they're the externally applied loadings. So what I'm gonna do on my diagram instead is I'm gonna label the nodal displacements and the nodal loadings. Okay, these are just general terms which could be anything. Okay, so let me draw them out first. Okay, so let's focus on spring 1. Spring 1, we have this node. Okay, first let's deal with the nodal displacement. So this labels as U1, and then node 2 is, okay, has a corresponding displacement of U2. Node 3 has a displacement of U3, and finally node 4 has a nodal displacement of U4. Okay, so these are just displacement terms that I assign to each of the nodes. Okay, so after you apply some loading conditions, these displacements will be okay. These nodes will displace, right? After you apply some loading conditions, these nodes will get displaced. So U2, U3 will have some value, okay, as a consequence of those external loads. Okay, then don't forget we also need to label the external loadings. Okay, so okay, so let's label the external loads with F. Okay, F1. Okay, then here will be F2, F3, and F4. Okay, the arrow that I drew, right, is pointing it will assign you the sign convention. Okay, the arrow means the positive direction. Okay, so that means rightward displacements are positive, and also rightward forces are positive. The arrow here shows the positive direction of the forces. Okay, yeah, so that's what the arrow indicates, is the positive direction of the forces. So that means I arbitrarily assigned rightwards as all positive for both forces and displacements. Okay, this is arbitrary, meaning it's a choice that you make. Okay, so now, what are these nodal displacement and nodal forces that I showed you? So F1, F2, F3, and F4, right, are just general terms for the forces that you can apply on each node. Okay, and then in a real scenario, for example, this one, you apply. Okay, you will use your hand or some loading device to exert a force on each node. Okay, for example, you see, in this problem, what they do is they exert P2 on node 2, P3 on node 3, and then there will be reaction forces at node 1 and 4. Yeah. Okay, so these are the externally applied loads. So that means in this problem, right, R1 is, sorry, F1 is actually R1. And then here, F2 is actually P2, and F3 is P3, and F4 is P4. Okay, so you don't label R1, P2, P3, P4 on this general form first. Okay, so this general form gives you a template to do your FEM problems. Okay, and then the question will provide you the external loads, namely, in this problem, P2, P3, R1, and R4. Then after we write out the global equilibrium equations, we replace F1, F2, F3, F4 with, R1, P2, P3, P4 respectively. Okay, so that's what I want to draw the difference between the Fs and the Rs and Ps. Okay. Okay, having said that, now we can begin to do our FEM. So what is the next step in FEM? After you draw the diagram, okay, let me recap. The first step is draw the diagram and then label the nodal displacements and nodal loads. Okay. The next thing you do is, okay, is the next step is stated in the question. The element equilibrium equations. Okay, so this is the next step. So what this means is, okay, you look at each element in your problem. Okay, how many elements are there in my problem? Well, there are 4 of them, right? 1, 2, 3, 4. For each of these elements, what you need to do is write down the element equilibrium equations. And this is very standard. Okay, in the lecture notes, we derived various element equilibrium equations for various elements. Okay, so the very basic element that we are discussing is spring elements. But later on in fact, the next tutorial, you will see other types of elements, for example, beams, trusses, conduction elements, pipes, and so on. Okay, so we're not interested in deriving here, or at least my series of videos will not discuss the derivation of those, but we're going to apply them. Okay, we're going to show you what's important, or I'm going to show you what's important, and then we will use them in FEM problems directly. Okay, so since we're dealing with springs, we have to use the spring element equilibrium equation. So what does that look like? Okay, so in general, if you have a spring who has nodes labeled 1 and 2, okay, so it has displacements u1 and u2 respectively. Then for this element, its equilibrium, its element equilibrium equation will look like this. Okay, so suppose it has a spring constant of K1. Okay, then this will K1 minus K1 minus K1 and K1. Then it's U1, U2. Okay, and then the stiffness matrix here, okay, this is what you call the stiffness matrix, will have labels on its heading, on its columns and its rows. Okay, so here's 1, here's 2, here's 1, and here's 2. Okay, and also you might see in the lecture notes there's this other vector here. This vector here contains the internal forces, but we're not really gonna deal with that. Okay, yeah, so that's not very important. So we're just gonna use the bare minimum of what we need for this question. So how do we use this uh element equilibrium equation? Okay, so whenever you see a spring, right, you will look at the spring and then you will apply this quote unquote formula. Okay, so this is what you can think of as a standard, okay, standard template for springs. For springs. Okay, so that means whenever I see a spring, I can just apply this formula directly. Okay, I'll show you for the various springs later, but right now I want you to know how to use this. So what is the 1 and 2 in the column and the row refer to? They refer to the nodes. Okay, so this 1 refers to node 1. This 1 also refers to node 1. This 2 and this 2 refers to node 2. Okay, u1 refers to this u1, u2 refers to this u2, and then the k1 that you see here refers to the spring constant of the given spring. Okay, so that's what these notations mean. Okay, that's what these notations mean. So let me clear all this highlighting. Okay, so this will be the element equilibrium equation, or rather the element stiffness matrix for uh, spring 1. Okay, in fact, we don't really need to care about the displacement vector here. Okay, we don't need to care about that until we write up the global equilibrium equation. Okay, so we don't really need to look at the displacement vector here for now. Okay. Okay, you know what? For completeness sake, let me just write it down. Yeah, but you don't have to pay too much attention to it. The next element, okay, so we already done the element equilibrium equation for spring 1. Now let's do it for spring 2. Okay, so spring 2, right, will look like this. So spring 2, the nodes are 3 and 4. It has a spring constant of K3. Okay, yeah, there's a spring constant of K3 according to the question. And then, yeah, okay, so what am I doing? I'm basically extracting out this spring here. Okay, I'm extracting out this spring here. Okay, so as you can see, its nodes are 3 and 4, and it has a spring constant of K3. Okay, so that means its nodal displacements is U3 and U4. Yeah, and then we can write out its element equilibrium equation. Okay, so the nodal displacements are U3, U4, and then the nodes 3 are 3 and 4, right? So I can label the column heading and the row heading with 3 and 4. 3, 4, 3, 4. Okay, then because the spring constant is K3, okay, so instead of K1, it'll be K3 minus K3 minus K3 and K3. Okay, so notice the difference between spring 1 and spring 2 here. Okay, so spring 1 has nodes 1 and 2. That's why the heading is 1 and 2. Its nodes are 1 and 2, so that's why its displacement is U1 and U2 here. Its spring constant is K1, so that's why all the entries here show K1. Okay, And on the other hand, for spring 2, its nodes are 3 and 4, right? So that's why the heading is 3 and 4 for the row in the column. Its nodal displacement is u3, u4. That's why in this displacement vector is u3 and u4. And the spring constant is k3. That's why inside these entries are k3 instead. Okay, so we're going to do that for the other springs. So let's go to spring 3 next. So let's take a look at spring 3. So spring 3 here is surrounded by nodes 2 and 3, and it has a spring constant of k2. Okay, so let's draw that out. Okay, so since its nodes is 2 and 3, its nodal displacement will be u2 and u3. And then, okay, you will write out the element equilibrium equation. So this will be u2, u3. This will be 2, 3, 2, 3. This will be k2 minus k2 minus k2. And okay, finally, we will do the same thing for spring 4. So spring 4 is surrounded by 2 and 3, also has a spring constant of k2. So actually, it's exactly the same as spring 3. So let's draw that out anyways, k2. So this will be 2 and 3. This will also be u2, u3. By the way, you don't have to draw these diagrams that I made out here individually. Okay, I just want to make it clear. Okay, so this is u2, u3. The headings will be 2, 3, 2, 3. And then okay, so the spring constant is k2, so it will still be like that. Okay, so these are the individual element equilibrium equations. What we're gonna do next is stated in the question. Okay, okay, we need to assemble. That is the next step. We need to assemble each of these element equilibrium equations into the global equilibrium equation. Okay, into the global equilibrium equation. Okay, global means the whole thing. Okay, the whole thing. Because right now we're dealing with the element on an element level, meaning each of the elements, element 1, element 2, element 3, element 4. But now, after deriving all the individual element equilibrium equations, we can combine them. Okay, in other words, we will assemble this. Okay, okay. In other words, we're going to assemble this and all these three other matrices, this, and this together. Okay, we're gonna assemble all of them together into a giant matrix. Okay, so how do we do that? So first of all, look at the nodes that we label here. So we have nodes 1, 2, 3, and 4, right? So that means we need to open a 4 by 4 matrix. So let's go ahead and do that. So on the heading, you write down 1, 1, 2, 3, 4. Likewise with the rows 1, 2, 3, and 4. Then here, following the stiffness matrix is the displacement matrix. So U1, U2, U3, U4. And then lastly, we have this vector. This vector will contain the external loads. So F1, F2, F3, F4. Right now, we're keeping things general. We're not substituting any values yet. Okay, we're not substituting any values yet. We will do that substitution later. For now, we need to focus on how to build the global stiffness matrix. Okay, the global stiffness matrix. Okay, so how do you do that? Take a look at your element matrices. So let's focus on the first matrix that we wrote. So how do you know where to put each entry? You look at the headings of the row and the column. Okay, they will tell you the corresponding position in the global equilibrium equation. Okay, what does that mean? For example, here we have row 1, row 2, okay, column 1, and column 2, right? Right now, I only want you to focus on the square matrix, okay, the matrix containing the case. Okay, so take a look at this K1 here. It belongs to row 1, column 1, right? So that means when you go back to your global equilibrium equation, you also need to go to row 1, column 1, okay, row 1, column 1 to substitute that k into that entry. Okay, so that means you put k1 into here. Okay, go to the next entry. So the next entry after that, the 1 1 entry will be hold on, this one. So row 1 column 2 is minus k1, right? So you go to row 1 column 2 and then you put minus k1. Okay, so you put minus k1 here. Next, you go to the next entry. So the next entry is row 2 column 1, it'll be minus k1. So row 2 column 1 is minus k1. And then lastly, row 2 column 2 will be k1. Okay, so you go to row 2 column 2 and then substitute in k1. Okay, yeah, so that's the first matrix done. That's the first matrix put into the global equilibrium equation. Next, we want to move the next one. Okay, so spring number 2. So you do the same thing. Okay, so K3, you put it into row 3 column 3. Okay, row 3 column 3. And then in the next one, okay, in row 3 column 4, you put minus K3. And then row 4 column 3, you put minus K3. And finally, row 4 column 4, you put K3. Okay, so let's go ahead and do that in one shot. So now we're focusing on entries on the columns and rows labeled 3 and 4. Okay, so here we have K3, minus K3, minus K3, and K3. Okay, now do the same thing for element 3. Okay, so we're done with this. Okay, now we're focusing on the what do you call this? The rows labeled 2 and 3, right? See, 2 and 3, 2 and 3. So as you can see, row 2 column 2 is K2, row 2 column 3 is minus K2, row 3 column 2 is minus K2, and row 3 column 3 is positive K2. Okay, so let's focus on rows 2 and 3 and columns 2 and 3 and then fill those out. Okay, but we have a problem, right? See, row 2 column 2 already has an entry, right? And that comes from this entry here. See, row 2 column 2 already has an entry, but the third element matrix tells us that we need to also substitute row 2 column 2 with K2. So whenever you already have a filled entry in your global stiffness matrix, what you need to do is just simply add that term. Okay, so we previously got this K1 from the first element matrix, right? Hold on, my laptop is lagging a bit. Okay, yeah, we got this K1 from the first element matrix, right? And then the third element matrix says we still need to put in K2 into row 2 column 2. So that means we just simply plus K2. Okay, so that's what you deal with overlapping terms. You just simply add them together. Okay, let's move on. So row 2 column 3 is minus K2. Row 3 column 2 is minus K2. Okay, and then you see here, row 3 column 3 already has an entry, but this matrix says that, hey, you still need to substitute in K2 into row 3 column 3. So we will just add it to the previous value, okay, the previously substituted value. Okay, now let's go to our last one. So now again, we're dealing with rows 2 and 3 and columns 2 and 3. Okay, I'm referring to this here, rows 2 and 3, columns 2 and 3. So again, row 2 column 2 we put K2, row 2 column 3 we put minus K2, row 3 column 2 we put minus K2, and row 3 column 3 we put K2. Okay, so as you can see, there's already some terms here, so we just put plus k2. Then here is minus k2, then put plus k2 here. Okay, so I'm going to simplify this. Okay, so k2 plus k2 is actually 2k2. Minus k2 is actually just minus 2k2. Same for here. Minus k2 is minus 2k2. And finally here we have k2 plus k2 is 2k2. Okay, so in symbolic form, this is our global equilibrium equation. What are we going to do next? Well, we're going to sub in all the known values that we know. Okay, so you see, they give us values in the question, right? So k1 is 10, k2 is 20, k3 is 30. Okay, and don't forget the forces that they substitute. They give us also. So P2 is minus 10, P3 is 20. Okay, so substitute all those values that you know into here. Okay, so if you do that, okay, if you do that, you will get, okay, so we have 1, 2, 3, 4, 1, 2, 3, 4. Then if you substitute, then it will be 10, minus 10, minus 10, 50, 40, minus 40, 70, minus 30, minus 30, 30. Okay, by the way, the empty entries are just actually zeros. You can write them down, but then just for clarity, I'll just leave them blank. And because I'm lazy to fill them up. Okay, so I'm gonna leave them blank, but if I leave them blank, it just means it's zero. Okay. Uh yeah. They told us what the external loading, right? They told us that there's a reaction force at 0.1. So this is R1. Also, there's a reaction force at 0.4, so also R4. Then they told us P2 is minus 10 and P3 is positive 20. Okay, now the question is, what are the displacements? And this is important because substituting the displacements, right, will have an effect in reducing the global equilibrium equation. I'll talk about what that means, but for now, let's focus on substituting the boundary conditions. Okay, so actually these are the boundary conditions. B, C, boundary conditions. So what is happening at the edge of the problem? So as you can see, nodes 1 and 4 are planted into the wall, right? They're fixed into the wall, they're built into the wall. Therefore, nodes 1 and 4 actually make no displacement, right? Even if you apply the load, they do not displace. Therefore, we can conclude that U1 is equal to 0 and U4 is equal to 0. So we can substitute those in, okay? So go to here, and then you make it the replacement. So U1 is actually equal to 0, and then U4 is actually equal to 0. Okay, so this is what you call the zero displacement boundary condition. Okay, this is a special kind of boundary condition which has a special effect on reducing the global equilibrium equation. Okay, what else did the question ask us to find? Okay, so here the answer they give us the displacements, right? So let's calculate for the displacements using this global equilibrium equation. So what do you do next? The next thing you do, right, is because the boundary conditions at 1 and 4 are 0, what you must do is you must reduce the global equilibrium equation. Okay, reducing literally means making it smaller. And what do you do? Okay, since node 1 has 0 displacement boundary condition, right? What you do is you cancel row 1 and column 1. Because node 1 has a 0 displacement boundary condition. Likewise, for node 4, since it has the 0 displacement boundary condition, you also cancel row 4, column 4. Because node 4 has a 0 displacement boundary condition. So what you're left at the end of the day, right, is only this, 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 and this. Okay, so copy those down. So the reduced form, okay, so reduced is, okay, so those happen at row 2 and 3. So you label the columns and head it, and the columns and rows as 2 and 3. Then you copy down the remaining entries of 50, 50, well, actually it's minus 40. Minus 40, minus 40, and 7. Okay, and what you're left is U2, U3, and okay. So actually, you see, your only unknowns are U2 and U3. You can simply solve this using algebra, or you can just solve this by moving this square matrix to the other side, right? If you move the square matrix to the other side, you will invert the matrix. Okay, so U2 and U3 will remain on the left-hand side. Then that square matrix will become inverted and then multiply with the 2 by 1 matrix here. Okay, so if you perform this calculation, okay, I recommend you use it in your calculator. If you perform this calculation, you will get 1 over 19 and 6 over 19, right? And that's the answer that they provided for us. Okay, U2 is 1 over 19 and U3 is 6 over 19, right? Yeah, see, this is correct, this is correct. And U1 and U4 are the zero displacement boundary condition, so it's correct. Okay, here's a tip for you to check whether you're on the right track when it comes to these FEM problems. Notice here in the global equilibrium equation, right? Okay, to check if you did things correctly, one hint is checking this matrix here, the square matrix here. Ask yourself, is it symmetrical? Meaning, are these entries mirrored along the diagonal to be exactly these entries? And it is, right? You see, well, minus 10, same as minus 10. 0, same with 0. 0, same with 0. Minus 40, same with minus 40. 0, same with 0. Minus 30, same with minus 30. So this stiffness matrix is symmetrical. If it is symmetrical, right, you are on the right track. Okay. If it is not symmetrical, something is wrong. Okay. You might have assembled something wrongly, you made a careless mistake, you made a careless calculation, or whatever. But the point is, usually this stiffness matrix is symmetrical. If it's not, it's a hint that something went wrong in the process of assembling the global stiffness matrix. Okay, so that's a hint to help you check whether you're on the right track. Yeah, so this is the first example of a FEM problem. I will do the next one in a separate video.